Okay, so before we get started, I did want to mention we have that Learn Smart assignment due Monday before we meet in class. That'll kind of set us up for the next thing we're going to be talking about. I will kind of also say on Monday we'll be doing some Excel work, mostly Excel work in class. So that's what's up and coming. I won't put an online quiz up today, so you'll kind of have this weekend with not one of those, just to get that Learn Smart done. Other than that, are there any questions from me before we get started? Okay. So, kind of left off last class talking about this standard normal distribution and how we look up different z-scores and find the area to the left of them using that table. So what happens if we start out with a variable, though, that's not normally distributed, right? So it doesn't have a mean of 0 and it doesn't have a variance of 1, but it still is a normally distributed variable. Well, then if I want to find the probability that this random variable x takes on a value in between, say, a and b, what would I do? Right? Well, the first step is we're going to transform that normal variable into a standard normal variable by turning those two values of a and b into z-scores. How do we do that? Well, we simply take that value, a or b, subtract the mean, and divide by the standard deviation. Right? Once we do that, we think about what region are we looking for? Well, it's the area in between these two z-scores, right? The x is in between a and b. We can look up the area to the left of each of these z-scores from the table, and then we might have a little bit of work to do kind of using those probabilities to find exactly what we want. So these are kind of the general steps, right? If I'm giving you kind of a visual to go along with this, not of me. Give us a second to switch over. Maybe. There we go. So what I'm thinking about is I have this random, this random continuous variable x. It's got some mean, has some variance, and I want to know, like what's the probability it's in between a and b. All right, so that's kind of what I'm looking for. Well, the very first step was turn these into z-scores. So here's my z-score for a, here's my z-score for b. We're still looking for the area in between. Once I have these, like let's say I calculate them, right? We use that z-score formula to calculate those two z-scores. I don't know, let's say they're negative 1.2 and 2.3 up here. What I can do from the table is if I looked up that z-score of negative 1.2, that would give me the area to the left here. If I looked up the area, or I looked at the z-score of 2.3 on the table, it gives me the area to the left of that. So now if I subtract that smaller red area from the larger green area, I'd be left with what I was originally looking for, which is just that shaded area in between the two. Okay? So that's kind of the general approach for all these problems that we're going to be working through. Right? We can always think about how are these values for x, right? A and b were the values for x. How can we transform them into z-scores, look up those probabilities in the table, and then a little bit of math at the end, right? Just subtract the smaller area from the larger area. Okay. Now that fourth step will be different depending on what areas we want to find, and we'll look at a couple different types of problems. Like so, let's say we put some actual values to this. Okay. So now I want the probability I'm in between two, not a and b, but what's the probability I'm in between 10 and 15? And it's this variable x that's normally distributed with a mean of 5 and a variance of 25. Okay. So what I'm doing is I can think about, I'm looking at this variable x. It's normally distributed, has a variance of 25, a mean of 5, and I want to know what's the probability it's in between 10 and 15, right? Right away, what do I know this area has to be less than? 0.5, right? Because the area to the right of the mean and to the left of the mean is 0.5, so I'm going to be finding something that's smaller than that. Right? Another thing I can do here is it sometimes helps to just not have the variance, but the standard deviation. So we end up with a standard deviation that's 5 here. Okay? So now I'm going to convert these values, 10 and 15, into z-scores. Okay? So the very first one, I'll take the formula for a z-score. I'll take the value of 10, subtract that mean of 5. That's a terrible looking 5, by the way. Subtract the mean of 5, and then divide by my standard deviation. Right? So divide by 5, I get this z-score of 1. So does that make sense? Well, a z-score of 1 means that I'm 1 standard deviation away from the mean, right? How far away from 5 is 10? 5. Right? What's my standard deviation? 5. So I'm 1 standard deviation above the mean, which sure enough should be a z-score of 1. If I look at this one, I could plug in the value of 15 and calculate that z-score. But if I just look at these values, how far away is 15 from 5, or from the mean? 10. Standard deviation is 5, so how many standard deviations away from the mean am I? 2. Right? Sure enough, if I plug everything into my z-score equation, I get that z-score of 2. Right? But with these easy numbers, it was kind of easier a little bit easier to see that. Okay? So the first thing I'm going to do is look up that z-score of 1, and it's going to tell me this area to the left here. I then can look up that z-score of 2. It's going to tell me the area to the left. Okay. Subtract the smaller one from the larger one, and I'll be left with kind of what's in between here. Okay. So how am I going to look up those z-scores? So I go to my table. Right. Scroll down here. 1.00. That's my z-score of 1. Right. So 0.8413. Or this kind of red area, right? 0.8413 is the area to the left of that z-score of 1. If I look up that z-score of 2, so 2.00, the area to the left of that is 0.9772. So I've looked up those two z-scores. Oh. There we go. Now the only thing left to do is subtract the smaller area from the larger area. All right, and I get that the area in between those two values should be 0.1359, which is smaller than 0.5, which we originally said, right? So at least it checks out there. Okay. Any questions on any step in that process? Any questions about that? Using the table or, okay. All right, so I kind of have here just everything we just did, right? We looked at those z-scores. I could then think about what region am I looking for? I drew that out. I looked up the area to the left of 1. I looked to the area to the left of 2. Look for the difference between those or subtract the smaller one from the larger one, and that led me to what was in between the two, okay? So it's just kind of a slide to repeat what all the work I did by hand here. I just think it helps seeing it drawn out. Oh, you guys can't see that, can you? Oh, is it just a blue screen? There we go. So this just has everything we worked through here, right? We looked up those two z-scores. We turned those values into z-scores. We found the area to the left of that z-score of 1, area to the left of that z-score of 2, subtracted the smaller area from the larger area, and we're left with what's in between those two values, okay? Or the probability that we saw something be in between 1 and 2 standard deviations away from the mean. Okay? So let's say we will look at some actual kind of data that has an application. So you can look at rainfall, and it follows pretty close to a normal distribution. So if I had this data for the last over 100 years in Excel, it'd be very easy to find the average or the mean and very easy to find the variance, right? We've got the formulas for that. So we could do that pretty easily, and see that this is a normally distributed variable that has a mean of 3.38 and a variance of 2.46. I can break this down by month. Kind of notice June rainfall is going to be able to have a little bit higher of a mean. We can look at, different months. We're going to see different means and different variances. If we kind of put this on a histogram or just try to get an idea about what the distribution looks like I said, pretty close to a normal distribution. A little bit something weird going on here, but pretty close. Okay? So we're going to treat it as though it's a normally distributed variable based off of the kind of graph we're seeing here. And in 2012, we had an extreme drought, right? Or we had a pretty bad drought in 2012. So rainfall was really low. There's all these areas that were, classified as extreme droughts. If we look at a time series, just kind of build up this idea, it's kind of interesting. Every time we look at like February and March in Indiana, we see this like uptick, right? This increase in rainfall. It goes back down in the winter months. We hit February, kind of March through June. Another spike, decreases in the winter months. Another spike until we get to 2012. And not only do we not see a spike, we actually saw it go lower, right? And so over that year, we had this average monthly rainfall of 1.3 inches, right? This is relatively low, right? Over that time, over that kind of summer, the rainfall was 1.3 inches. So what's the probability, given the mean and the variance of rainfall in Indiana, what's the probability we actually saw it be as low as it was in 2012, or 1.3 inches, or anything lower, right? Anything below that. So let's see if I can remember all these values. So we've got the setup that we should be thinking about right away is that we have this normally distributed variable x. The mean was what? 3.4. The variance was 2.57. Okay. We wanted to know what's the probability we saw 1.3 inches of rainfall or less. Right. So what I'm going to do is turn that value of 1.3 into a z-score. So how do I do that? Right, I take that value of 1.3, I subtract the mean, I divide by the standard deviation. Well, I only have the variance here, but to get the standard deviation, I know that that's just the square root of the variance. Okay. I think if I remember, no, I'm not probably going to remember this correctly. I think it's negative 1.31. Okay, yeah, if we plug everything in, we get negative 1.31, right? So, and that makes sense. It should be negative because we were below the mean, right? So we're going to be a certain number of standard deviations below the mean. We just have this weird one where I chose I ended up having this value where the z-score actually isn't much different than what the original kind of x value was. That doesn't necessarily have to be the case, and we'll see this in the next example we do. That doesn't have to be the case. So I'm looking for the area to the left, right? So I'll look this up on the table, and the table will give me the area to the left. So here I don't really have a step 4. I don't have to transform the probabilities or use the probabilities. It's just what I look up, right? So we go to the table. I'm going to look up negative 1.3. And I believe the second column is 1, but let's just double check. Oh, yeah. So 1. So negative 1.31. The area to the left is 0.0951. Sorry, guys. Why is that? How long has it been like this? Oh, okay. That switched out. That's the cable. Or something. There we go. Oh, come on. All right. we had some technical difficulties here. So where was I? What was I saying? Oh, we're going to look up that negative 1.31. So the area to the left of that is 0.0951. So we found this was 0.0951. Then we're done, right? This one, there's no fourth step, right? What we're probably looking for was exactly what we could get from the table. Okay. Any questions on that before we keep moving? All right. So let's think about a different one. So let's say we have kind of just September rainfall, and this last September was actually, this is what prompted this example. There was like no rainfall at all, to the point where it was like I started to wonder about what it actually was. So I looked it up, and it actually ended up being less than half an inch, right? 0.47 inches of rainfall. We've got a mean and a variance. They're a little bit different than the kind of total, but for September, the mean's a little bit lower and the variance is a little bit lower as well. So we could actually look for the probability that we saw rainfall be as low as it was or anything lower. And you can imagine, like for someone, a large, if you're farming or kind of producing some type of agricultural product, you might want to know how likely is it I get this little amount of rainfall, because if that's the case, I'm not going to be able to produce the product I need to produce. Right? So let's go here and think about if I had, actually, kind of read these things through it. So I'm going to try to get, there's just white paper underneath there. And hope that I brought a little bit more because I'm apparently used all this up. So the setup we have is we have this variable x. The mean was I already forgot what it was, 3.25 maybe? Yeah, 3.25. We have a variance of 2.37. What's the probability we saw 0.47 inches of rainfall or anything less, right? Well, just looking at this, I mean, our standard deviation is going to be the square root of 2.37, which I think, I'm going to use Excel to do the math for me here real quick, but I think is what I had earlier. Yeah, 1.54. So the standard deviation is 1.54. So how many standard deviations away from the mean am I? Well, I'm almost 3 away, so I'm almost 2 standard deviations away here. Right? I don't know what the exact z-score is, but I'm going to be at almost 2 standard deviations below the mean. If I had to guess, around -2 is the z-score here. But we can actually map this out to whatever the z-score is by taking that value, subtracting the mean, and dividing by the standard deviation. So see, kind of here, calculating it ahead of time made it a little bit easier when I was plugging things in here. And I think if we do this one, we get -1.81. So I could then look that -1.81 value up on the table. The table would tell me the area to the left. That's what I wanted. I'd be done. Right? So sure enough, I'll look up negative. So here's the one, -1.81. So that probability is 0.0351. So the area to the left of that z-score, 0.03, did I say 51? Yeah, 51. Just kind of identifying that there, right? Any questions on that before we keep moving? I hope I've got a little bit more paper in here. Yeah, here's a little bit. I thought I had a bunch. All right. So let's go, and we kind of have our view of what I just talked about here on the slide. It's basically what I did by hand. I think it just helps seeing it kind of drawn out by hand. So we can do the same thing instead of rainfall. We can do it with temperature. Temperature follows pretty close to a normal distribution. Now, the problem with temperature is if you just do everything, if you graph this out for like every month, then it doesn't. There's just too much variation. But if you look within kind of any 1 month, like you get some pretty nice normal distributions. So here we've got like June temperature and the variance in June temperature. We compare that to February. So like much lower average temperature in February, but also much more variation if we look at it, right? So some years it's colder, some years it's warmer. So let's say we wanted to find, we've got the average June temperature is 70.75. We've got the variance. What's the probability that this June it's warmer than 71.4 degrees on average? So we can draw this out. So what we're looking for here is we've got this variable x, which represents temperature in June. The average is 70.75. We were asked to find the probability that's greater than 71.4. And I think the variance was 6.3. So once again here, it might help to think about what's my standard deviation. So what's the kind of square root of 6.3? I think I have this one in Excel as well. So let me double check. Yeah, 2.51. So approximately a standard deviation of 2.51. I'm not even 1 away from the mean, so I'm way less than a half, I'm less than even a half of a standard deviation away, right? So we should end up with a pretty low z-score here, which means I probably drew this out of scale, because if the z-score is relatively small, well, the z-score of the mean will always be 0. So if I'm not many standard deviations away from 0, I'm going to end up with a z-score that's pretty close to 0. Right? So if I'm like mapping this out, I probably should have drawn it like way over here, right? It's kind of hard to know like proportion-wise how to draw these, and it's okay. You never have to like have it drawn out perfectly. So let's just kind of keep it where we had it. But we know the z-score is going to be relatively small, right? So how do I find that z-score? I take the value I'm interested in, 71.4. I subtract the mean, and then I divide by, oops, right here, my standard deviation of 2.51. Right? I think if I do this, I get, I want to say this is negative 0.259. Let's double check the slides, but I think that's what it is. Yeah. Oh, not negative. What am I doing? Of course it can't be negative. Why could it not be negative? I had a value that was above the mean, right? So I had positive 0.259, which is going to present a problem to us because once we go to the tables, we can't use that 0.259. We have to keep to the second decimal. So I'm just going to round this and use that z-score of 0.26, okay? Now when I go to the table and look up 0.26, the table will tell me the area to the left. I want the area to the right, so what am I going to have to do? Yeah, just subtract that from 1, right? Whatever the area to the left is, I know the area under the curve is 1, so these two things have to be complements, so I can just subtract it from 1. So we'll look up that z-score of 0.26, positive 0.26. We'll so scroll down, 0.26, so 0.6026. Right? So I've got the area to the left is 0.6026. I'll subtract that from 1, and I end up with what? 0.3974. Okay. Now, right away, once I saw that there was something above the mean, I knew that the area to the right of that has to be less than what? 0.5, because the area to the right of the mean is 0.5. So I'm looking for an area smaller than that. So right away, we could have ruled the answers down to, I believe it's A and D. Right? Those are the only two that were less than 0.5. But once we ultimately find the z-score, look it up in the table, sure enough, we get something that's less than 0.5. Okay. Any questions over any of that? Okay. Let's do one more here before we move on to the next idea. So let's say I have the exact same setup. I'll go through this one a little bit quicker. Let's say I have the exact same setup, but I'm thinking about February temperature has a much higher variance, right? If I'm thinking about it here, a variance of 26 means the standard deviation is approximately what? It's going to be pretty close to 5, right? 5 times 5 would be 25. So, right, going to be close to a standard deviation of 5. I'm looking at something that's more than 10 away from the mean, right? 43 degrees is more than 10. So, you know, I'm thinking about something that's at least 2 standard deviations or around 2 standard deviations here at the very least. That's just some rough math, rough rounding. Now, what I think about here is I want the probability it's great that the temperature, I guess this February is already over, but the next February that the temperature is kind of beats 2017, right? What's the probability it's 43 degrees or greater? I'm really thinking about the same setup here. It's just that now, right, my mean is like 28. I'm looking at this value of 43. My standard deviation, if I have anywhere to write it, there we go, is approximately something around 5. So it's like, well, this area is going to be relatively small. We know it definitely has to be less than 0.5 because it's still something above the mean, right? But really, it's going to be the exact same process. So if I find my z-score, right, by plugging in the value I'm interested in, almost 43, the mean, here this I could use the standard deviation, or I just could put in the square root of the variance. It's the same thing. I actually get a z-score of 2.73. So that's pretty far away, right? 2.7 standard deviations away from the mean. So the area to the right of that should be really close to 0, right? We think about, well, if I was doing it on this graph, just for a second, the higher up my z-score gets, the smaller the area to the right of it gets, right? So 2.73 is pretty far away. Sure enough, if we look this up, 2.73, 0.9968. Well, that's the area to the left. I want the area to the right, right? I want it probably being greater than that. So whatever, right? Similar to what we had here, we had like 0.99 to the left. We'll subtract that from 1. Okay. So we'll go back here, and we subtract that from 1, and we get about 0.0032. So because it was so far away from the mean, it's very unlikely that we see something that far away from the mean or further, right? In fact, there's only a 0.32% chance that this next February will be warmer than the February in 2017. Okay. So you could really do this with any month or any rainfall or temperature. And we'll do more of that in Excel on Monday, work with that Indiana weather data file. Any questions on that? I went through that in a little bit quicker, but it's because I want to make sure. So I want to kind of dive into this next topic, which is the inverse transformation. Okay? So we start out, we have this equation that gives us the z-score, right? So if you tell me a certain value for x, I can tell you the probability you saw that value or anything below it, right? Or the probability you saw that value or anything above it, right? I can start with that x value and find you the probability. But what if instead I know the probability I want and I want to find what cutoff value for x would give me that? So I'll kind of go through it, the general idea of what we're doing. So before, we were starting out with this value for x. I don't know why I drew that like this. We were then converting that, right, into a z-score. And then from that z-score, we were finding the probability that z, was equal to that or something lower, right? Z was less than or equal to this specific z-score. What we're going to do now is say, okay, well, look, what's the cutoff maybe for like the 90th percentile? So I know the probability of the area that I want to the left is 0.9, with the inverse, we're going to work in reverse, find the z-score that gives us 0.9 in that left tail. Once we have that z-score, we can work backwards to solve for what that cutoff value of x would be that would give me that desired area in the tail, or does it give me that desired probability of being less than that specific value. So we're going to be doing everything in reverse from what we were doing before. Right? So what is that going to look like? Let's work through some actual numbers. So first of all, we'll take that z-score equation, and now we're going to solve for x, right? Because if I have a certain area that I want in that left tail, I can find the z-score that would give that to me. If I would given the mean and the standard deviation of this variable, then I can plug those values in and solve for what that cutoff, or what x value would give me, say 90% in that lower left tail. So let's work with some actual numbers. So we'll do this test score example where I've got what? An average, the average on this exam is a 72. The variance is a 64. So what was the lowest score that would put me in the top 10% of test scores here, takers? So what we're thinking about is I've got this standard normal distribution. I want the z-score that was the cutoff for the top, 10%, which means it was also the cutoff for the bottom 90%, right? So I want the z-score that's associated with having a cumulative density of 0.9, right? Or the area to the left of it is 0.9. Okay. So now that I know that, I can look up in the table what that z-score would be. Okay. Once I have that z-score, I can plug into that inverse transformation function some different values to solve for the cutoff, right? The test score that would give me 90% to the left. Right? So how do I find that z-score that's associated with having an area of 0.9 to the left of it? Go to my table. I'm no longer going to use the row and column headings to look up a z-score, right? I don't have one, right? The thing that I have is the area to the left, or the probability of seeing this certain z-score I don't know yet, or anything below it, and I know that's 0.9. So I'm going to hunt through here what's closest to 0.9. Looks like it's these two values. Right? So that's as close as I can get. So somewhere in between 1.28 and 1.29. Anytime we're in between two like this, like I can't find exactly 0.9, we'll take the higher of the two, or in absolute value, the higher of the two. If we're doing negative numbers, kind of ignore the negative sign, but take the higher value. So between 1.28 and 1.29, I'll use 1.29 as being the z-score that would give me 0.9 in that lower left tail. So 1.29 here. I then look at that inverse transformation formula. Right. The mean was 72. The z-score is 1.29. If I recall, the variance was 64, which means I have a standard deviation of what? 8. Yep. If I plug this in, I should get approximately 82.3 something, I think. Okay. All right, so basically using this formula, after I find that z-score, I can determine the test score that would be the cutoff for the top 10% on an exam like this would actually be as low as an 82. Okay. So
I didn't get that.
Oh,
you can also try.
I guess I said Siri somewhere there, or whatever it is. So sorry about that. I'll jump down on my skin. One thing is, if we're looking for that top 10%, we automatically knew, right, that it has to be something that's above the mean, right? Because the mean would be the cutoff for the bottom, or for the top what percent? 50, yeah. So I automatically knew it had to be something to the right of the mean. Sure enough, quite a bit higher than 72. Right? Any questions on anything there? All right, let's go back here. And I kind of have all the steps on this slide and everything that we did. I just think it helps seeing me kind of work it out by hand. So we have a very similar example, but instead of kind of the top 10%, I want to know what's the cutoff for the bottom 40. Right? So, you know, maybe like what's the kind of test score such that I'd be in the lowest 40% of test scores? Well, first of all, a negative test score in the context of this example doesn't make any sense. Also, if I'm thinking about the answer of 0.26, if someone actually got that result on a test score and the average was 72, what would a test score of 0.26 be the cutoff for? What percent would be below it? Approximately, if I'm looking at, like if I'm thinking about 0.26 as the cutoff as a possible answer for being the cutoff score for the bottom 40%, doesn't make any sense, right? A test score that low would be like the cutoff for the bottom like 1%, right? So C and A just don't make a lot of sense in the context of this example. Also, you know, we'll talk about why we can actually rule 74 out as well in just a second. So how would I set this up? So I'm looking for the Z value, first of all, that gives me 0.4 in this lower left tail. We already said what's the cutoff for the bottom 50%? Would be a Z-score of 0, right? Like the mean. But you're right. If you're thinking about what would be for the original X variable, what would be the cutoff for 50%? That was our mean of 72. Yep. Sorry, I was looking at the standard norm of the Z-score distribution here. So I know that the test score that gives me 0.4 to the left should be something that's lower than 72. So I think the only one that really makes sense there was the answer of 69.9 or whatever it is. But how can I actually solve for that, right? If this is a short answer or I have other options that make sense. Well, so I know the area I want in the lower left tail is 0.4. So I go to my tables. I don't look up 0.4 here because I don't have the Z-score. I know the area I want in the tail. So I know I want 0.4, so I'm going to look it up. Looks like it's in between these two. It's as close as I can get. So negative 0.2, scroll up, 5 and negative 0.26. So here, taking the higher and absolute value of the two, negative 0.26. Okay. So I just looked this up. This is negative 0.26. From there, it's just a matter of plugging our values in. Right? I think we still have the variance of 64, which is a standard deviation of 8. So if I write out the inverse transformation formula, I've got everything I need. Just be careful. There is a negative sign here, right? And I think the answer is 69.92. We end up working it out, right? So we map this out. This was this value up here, or the cutoff, the score that would be the cutoff for being in the bottom 40%. Okay. Any questions on that? We're okay with this? All right. So it's really just doing everything in reverse, right? Instead of starting with an X value, turning it into a Z-score, looking at that Z-score up and finding the corresponding probability, we find the probability, find the corresponding Z-score, then using that Z-score, plug it into the inverse transformation formula to figure out what that cutoff score for X is. All right. So that's kind of what we did here. We'll save this for Monday. I think that's all I actually want to do there. So unless there's any other questions. Okay. I'll kind of leave you with this Z-score pickup line. So if hotness was a normal distribution, you'd be 3 standard deviations above the mean. I always actually want to change this. I just stole this from someone else, but it should be if you would be a Z-score of 3, and if they don't get that the Z-score of 3 is high, then that, just walk away. But so that's always one of my favorites. I think you should be good. I'm not doing an online quiz this weekend. So you should just have that Learn Smart to make sure you get that done before we meet on Monday. And you can take a look at that Connect assignment. It's going to have a due date pretty far off in the future, but if you want to get an early start on that, I'm going to get the next Connect assignment posted this afternoon as well. Okay? All right. You guys have a good, fun, safe weekend, and I will see you on